Hey everyone, and welcome back to this class. This is a short lecture I like to give in each of my courses on how to succeed in this course. This is very important to talk about because you're learning a difficult technical subject. It's easy to get stuck, or even worse, give up because you're just not getting things. Maybe there are too many gaps in your knowledge, so you can't connect the dots. Maybe some assumption you've made is incorrect. And keep in mind, there's a lot of material in this course. It can be overwhelming if you're new to this field of study and you're not familiar with the conventions and the typical patterns we use. Now, if you've already seen this lecture in the past, you are more than welcome to skip it if you remember what's in it and you're already using these guidelines. The first guideline is this. Remember that I want you to succeed. In fact, that's why I'm giving you these guidelines in the first place. So if at any point when you're watching these lectures and you become confused, just ask on the Q&A, also known as the discussion forum. Typically, I respond within hours, sometimes even within minutes if I happen to be on the site and I see a notification. I answer any and all questions, so even if you think it's stupid, just ask anyway. One example I get from time to time is, where do I get the code for this course? And of course my answer is typically, well, it's in the lecture called Where to Get the Code for This Course. At the end of the day, no one cares if your question was trivial or silly. If it's something keeping you from progressing in the course, I want to answer it. Now, very rarely I get people saying, well, I was so confused that I couldn't even think of the right question to ask. And this is where you have to take some responsibility for your own learning. You have to ask yourself, what did the instructor assume I know that I didn't actually know? Maybe I can look into those things, and that will help me formulate a question. Maybe there's some background knowledge I'm missing. A lot of people like to have exercises to practice when they're taking a course. The act of thinking of the right question to ask is itself an exercise. It might not be the type of exercise you thought you'd be doing, but in many ways, this is more profound. This is an exercise that requires you to think and to change how you think. And ultimately, that is the best value you can get out of a course. Speaking of background knowledge, this is one of the most important guidelines in this lecture. You may have noticed that in the course description, I've listed some prerequisites, or in other words, things you should know before starting this course. Now you might wonder, why do I ask you to know these things? Why don't I just teach them in the course? And while we do review some topics in this course, it's not the focus. There's such a wide variety of students in this course. Students from almost every country in the world. Students of all ages. Students of all backgrounds. What does this mean? That means what's review for one person is going to be totally new for another. Some people are going to tell me they don't know calculus. Some people are going to be very far behind with their Python programming skills. But if we start teaching Python programming skills, other people are going to say, hey, why are we doing Python? Isn't the topic of this course deep learning? And I tend to agree that we should stay on topic. So how can we reconcile this? Well, it doesn't make sense for me to give you an entire computer science education in this one course, because a lot of that would be irrelevant for a lot of people. The only logical thing to do is for all of us to meet at a common meeting point. How is that point defined? Well, it's defined by the course prerequisites. In fact, they are so important that in certain instances, I've listed the course prerequisites twice, just in case you missed it the first time. And I'm also reminding you now for good measure. Now, one pitfall is that people sometimes assume they know things that they don't really know. So if you took calculus 20 years ago and you got a C, and you skipped class, and the times that you did show up for class you were sleeping, well, probably you don't know that much calculus. But remember, I want you to succeed. I want you to be able to learn this material. I can point you to resources where you can pick up this missing background knowledge, but the key is you have to ask. In some cases, there are certain places where I'm not allowed to post certain links, so we have to be mindful of the rules of the platform we're using. Now, occasionally people ask me, well, why don't you just teach a course for pure beginners? Why don't you teach these courses in such a way that they don't require lots of math and lots of prerequisites? Well, I don't want to turn this into an easy beginners type of course, because for one, that's not what I'm interested in personally. And number two, don't forget that this is state-of-the-art stuff. State-of-the-art generally isn't easy, and if it were easy, that would mean everyone is doing it. And if 1,000 other people can do the same thing as you, well, what's a potential employer going to think? What are your chances of getting that job when all 1,000 of you have the exact same skills? So we don't want skills that are easy to get. We want skills that are hard to get. Skills that put you at the top of your game. Skills that not many people have. If I'm hiring someone, I want the guy who stands out, not the guy who says the same thing as everyone else. Finally, the final guideline for how to succeed in this course. I mentioned earlier that there's a lot of material, so much that it can be hard to keep track of. In addition to taking your own notes and doing all the derivations yourself, how can you be absolutely sure you're understanding this material? I would in fact consider this even more important than the derivations. Not everyone is going to be a pro at math, so it's understandable if you want to skip a few steps. Sometimes it's possible to compartmentalize some concepts or delegate learning them for some other time, but still understanding the high-level picture and how it fits in with everything else. What you cannot skip is the implementation. Implementing these algorithms in code is the real test for whether or not you understand the material. And this is not about reinventing the wheel or that you shouldn't roll your own whatever because someone else out there can do it better than you. That is a software engineering principle, not a principle of learning. In production, you don't want to write your own hash map or your own string class. And yet, what do we usually do as an exercise in a typical intro to computer science class? Well, we do precisely that. We implement hash maps and we implement strings. And why do we do this? Because we want to have a better understanding of how these things work. If you make an assumption that's incorrect, well, your code is probably just not going to work. Merely using a hash map and using a string only gives you a very superficial understanding. That's beginner stuff. That's stuff everyone knows. That's not stuff that's going to help you stand out from the competition. And it's true that you'll never use your own homemade hash map or your own homemade string in any code you write, unless of course you are a professional that focuses on that sort of thing. They'll probably be inefficient and they'll probably have bugs, but that's okay because you're not doing it to make it perfect. You're doing it to learn. You'll notice that the general pattern that this course follows is that we always discuss theory, and then we implement that theory in code. So we're always going from theory to code, implementing everything that we learned. If you can, try to implement something before watching the coding lecture. In the appendix, I have a lecture called How to Code by Yourself that goes much more in depth into this topic, along with multiple strategies for how to approach implementation exercises. So to summarize, these are the guidelines I think are going to help you succeed in this course. Number 1, make generous use of the Q&A, even when you can't think of the right question to ask. Number 2, make sure you meet the prerequisites to this course. If you're not sure what they are, or you're not sure how, see guideline number 1. Number 3, try your best to implement everything we learn. This is the true test for whether or not you understand something. Remember that it's perfectly normal to get stuck once in a while. I get stuck all the time when I'm learning. That doesn't mean I'm not smart, nor does it mean the book or video I'm learning from is bad. It means that there's a disconnect between what the author believed I knew and what I actually know. And as a learner, I do my best to close that gap. A good skill to have is learning how to compartmentalize concepts. So here are the things I understand, here are the things I don't understand, but here are the things I understand about the things I don't understand, and these are the holes. So you know what you're missing and you know where they fit, and you can work to fill in those gaps over time. One thing I've been doing quite a bit recently is adding review lectures to my courses. These aren't meant to teach you everything from scratch, since that's going to take you a long time, but they are meant to help you recall certain things you may have forgotten. So if you have an idea for a review lecture that you'd like to see added to this course, please feel free to make a suggestion using the Q&A. Hey everyone, and welcome back to this class. This lecture is designed to answer some common questions I get about how difficult this course is and where it fits in terms of academia, the professional world, and its practical applicability. So rather than answering this question individually over and over again, it seems like a better idea to make a lecture about it and answer everybody at the same time. A lot of people become confused because this is their first machine learning course and they just don't know where it fits in the grand scheme of things. So is this course academic or practical? And is it for beginners or experts? Is it fast-paced or slow-paced? I'm going to answer the second question first. Is this course for beginners or experts? Interestingly, the problem with this question is a problem for machine learning too. Let me explain why this question is itself problematic. One of the challenges in natural language processing is that of ambiguity. When someone says some words, the problem is those words can mean multiple things. And it just so happens that I have some courses on NLP, so this is a problem I think about often. So how does that apply here? Well, when we use the words beginner and expert, we have to ask, a beginner from whose perspective? An expert from whose perspective? For some of you, you might think that a beginner is a random person you take off the street who knows nothing. But even that is ambiguous. There are people out there who do not even really know how to use a computer beyond turning it on and checking their email and browsing the web. There are people out there who are pros at Microsoft Office, so they know how to use a computer and make a Microsoft Word document or a spreadsheet, but they've never done any programming before. There are people out there who are very good developers and have lots of programming experience, but they have no idea what machine learning is. So all of these people are beginners in some way, but each of them would require a vastly different amount of work to prepare for this course. It's the same situation with experts. Most people consider anyone who knows more than them to be an expert. But of course, how much you know and how much some other person knows is relative. If you know how to plug and play into scikit-learn and nothing else, you might seem like an expert to someone who only knows Excel, but you'll seem like a beginner to someone who's read Bishop's Pattern Recognition and Machine Learning book. So just to finalize our answer to this question, is this course for beginners or experts? This question is misinformed to begin with because beginners and experts are not well-defined terms. Instead, we have to go back to what is the specific skill set you need before starting this course. And of course, that's defined by the prerequisites which are listed in the course description. So precision is the key here. We want to know what is the precise list of skills that I need before taking this course. This is much better than ambiguous terms like beginner and expert. Another matter is that people are going to measure their own skills differently. That's a much tougher issue to deal with. Sure, I can say you need to know Python coding before starting this course, but you can be sure that there's a big difference between someone who just learned Hello World and for loops versus someone working at a big financial institution. Now, even in those big financial institutions, there could be big gaps in performance. Even within your own team, there can be big gaps in performance. I've seen guys who've been working for 15 years do worse than guys who've been working less than 1 year. So even if I say you need to know Python coding, there can be a lot of variation in skill among those who consider themselves good at it. A similar situation happens with deep learning. I can say you need to know how neural networks work. But there's a big difference between someone who can code them from scratch and has experience using them versus someone who just watched some online animations for a few hours. If you had to bet on who knows neural networks better, who would you pick? So to really answer this question, we have to turn to the course itself. If I say you need to know Python coding and you claim that you do, but you don't understand some Python code in this course, then simply put, your Python coding skills are not yet up to par. So you have to improve your Python coding skills by asking questions on the Q&A and taking the appropriate steps to cover your gaps. Quite often, I get people who are just too confident in their own abilities, when unfortunately the reality is there is a huge discrepancy between what they think they know and what they actually know. What's funny is these people sometimes say, this course requires PhD math. I assure you, there is absolutely no math in any of my courses that requires a PhD or that only a PhD can understand. My courses contain only undergraduate math at most. Sometimes people even claim to have a PhD and then claim that it's still too hard, which is funny because that essentially invalidates your entire PhD. The entire point of a PhD is to turn you into an independent researcher. And so if you're supposed to be at the level of doing independent research, but you can't understand some undergraduate math, well, that's not very good. Essentially, what it boils down to is people are really trying to say, everything I don't understand is not important. Everything I do understand is important, and therefore, everything you say that I don't understand, I don't need to know. You can see why this thinking is dangerous. If you truly believe that everything you do not know is not important, then you'll never learn anything new. Now this brings us to our third question. Is this course fast-paced or slow-paced? And I think you can see where I'm going with this. This is yet another example of ambiguity. Fast-paced to whom? Whether it's fast-paced or not depends on which person is taking the course. So if someone is well prepared, then things will be just right. If someone already knows most of these topics, then it will probably be too slow. If someone chose not to prepare for the course, or they have an inadequate understanding of the prerequisites, then it's going to be too fast. So if I expected you to know something and you didn't, then you have to look it up, which is going to make the course feel like it's going too fast. So here is the real test. If I say something depends on calculus and probability, and you claim to know calculus and probability, but you don't understand the thing that depends on calculus and probability, you have to ask yourself honestly, do I really understand calculus and probability? Or did the instructor invent his own kind of calculus and probability that I don't yet understand? Well, of course, that's not very likely. It's most likely that you thought you understood calculus and probability, but you really don't. Now on to our initial question. What kind of course is this? Is it academic? Is it for professionals? Is it practical? So to understand this, you have to understand where machine learning is usually taught and how it is usually taught. Firstly, machine learning is usually taught in upper year computer science and engineering programs in university and college. So these are students who already took calculus 1 to 3, linear algebra, differential equations, probability and statistics, discrete math, programming, and possibly more, all in their first 2 or 3 years of college. So by the time they get to 3rd and 4th year, they know all this stuff and they're ready to apply it. So a typical academic course might cover a whole library of machine learning algorithms. So you might learn k-nearest neighbor, logistic regression, k-means clustering, PCA, and so on, all in the same course. Typically, you'd cover one algorithm per lecture, which is about 2 hours. Overall, you might have something like 12 or maybe 20 of those lectures in a term. And by cover, I mean mostly via math, geometry, and derivations. These courses don't typically have you at your computer doing programming work. If you do end up doing programming, it's usually part of a lab assignment, which is actually just a very small part of the course, compared to the rest. So it's mostly theoretical, dealing with equations, solving equations, reasoning about equations. Those equations typically involve probabilities and information theory. So you have 2 hours to go through the theory for one algorithm, and then if there's coding involved, which there usually isn't, you do it on your own time. The lectures themselves do not involve any coding. But there's an even bigger problem with these academic courses, and what is that? What happens is that the grades turn out to be very low. Out of 100%, the average might be around 25% or up to 40%. Now you might think, wow, so everyone fails. And of course that's not the case, since everyone gets shifted based on the average. So what is the real problem here? A lot of people ask me, well, why don't you cover every machine learning algorithm in one big massive course and just call it machine learning? Well, the answer is that if you try to do too much, you only end up understanding 25% of the material, which I think is clearly demonstrated here. And as they say, the proof is in the pudding. If you look at these courses where students are trying to digest 10 different algorithms at the same time, what is the result? The result is they don't understand any of them. If you try to understand too many things, you end up understanding nothing. I take the perspective that if you're going to take a course, you should aim to understand 100% of the material. Each course is broken up into appropriate levels based on how difficult they are and by topic. So for example, you can typically take Calculus 1, which focuses on differential calculus, Calculus 2, which focuses on integral calculus, and Calculus 3, which focuses on multivariable calculus. You would never learn all of these in just one huge course called math, because that's just too much stuff to understand all at once. I want you to understand 100% of the material. Even 50% or 75% is not good enough in my opinion. If you only understand 75% of the material, and the next course depends on the 25% that you didn't understand, well then you're not going to make it to the next level. Now let's look at the opposite end of the spectrum, what most people might consider to be a practical course. I don't consider these to be practical courses, and I'll explain why later. But I'll use the word practical here in quotes, since that's what some of the more beginner students will refer to them as. So how does a practical course typically proceed? Well, first, you are never really taught how the algorithms work, other than at a very high level. You might learn how they work by way of analogies and metaphors. So for example, suppose you're learning about gradient descent. Well, the instructor might relate this to a ball rolling down a hill. Now some beginner students, they might conclude that I understand a ball rolling down a hill, therefore I understand gradient descent. But they neglect to understand how to take derivatives, they neglect to understand how to choose a good learning rate, and most importantly, they neglect how to implement gradient descent in code. So it's totally wrong to assume that just because you can visualize a ball rolling down a hill, that you understand gradient descent. Why? Well, the problem is, everybody can imagine a ball rolling down a hill. Your grandparents who can't even turn on a computer can understand a ball rolling down a hill. So don't equate understanding an analogy to understanding the real topic. So what's the next thing these practical courses do? The next thing they usually teach you is how to plug into an API, or in other words, make use of a library someone else wrote. This is also not ideal. Typically, this involves just 2 or 3 lines of code. You have to wonder, if machine learning just boils down to 2 or 3 lines of code, why is it such a big deal these days? Why did it take decades for people to realize its usefulness? And of course the answer is that there's much more to machine learning than just these 2 or 3 lines of code. When you use a deep learning library like Keras, you're not doing deep learning. You are using a deep learning interface. You're simply programming. It's more accurate to say, I can program with deep learning libraries, rather than saying I actually know deep learning. But some of you might say, well, that's all I really want to do. All I need is an API, and for the API to give me an answer. I don't care about how it works. But then here is where you run into trouble. Recall that in addition to all data is the same, we know that all machine learning interfaces are the same. So the question becomes, which API do you choose if they're all the same? How can you make an informed choice about which one to use? Well, the reality is, if you don't know how these things work, then you can't answer this question. This is why some of these so-called practical courses can cover 20 algorithms in the same course. It's because they never actually talk about how the algorithms work. Since the API is the same every time, it's very easy to just do the same thing 20 times and then not bother with the details. So this gives people a lot of confidence that they were able to do the same thing 20 times. But it's dangerous thinking because you don't realize you really only learned one thing, you just repeated it 20 times. So how about when it comes to the professional world? Sometimes people tend to believe that in your profession, you'll be leaning more toward the practical end of the spectrum, where you don't really need to know how a machine learning model works, you just have to know its API. But what it really comes down to is what your job actually is. If you're a regular everyday programmer and you just want to see how a machine learning model might perform on your data, then you're going to use a pre-built library most likely. That's just the 2 or 3 lines of code I referenced earlier. However, that does not mean you don't still have to conform to best practices, make sure you're not mixing your test set with your train set, make sure you're doing proper validation, and so on. And when it comes to tuning your model, then you'll have to be able to dig down into the details and see which hyperparameters are possible to change and which are likely to have the most impact. So only knowing how to use an API is only going to get you past the first stage. You can plug in your data and at least your code has the right syntax and doesn't crash. But of course, your code not crashing doesn't necessarily mean it's right. Back on the other end of the spectrum, you have programmers and scientists whose sole job it is to do machine learning. These guys are machine learning experts. They know the math inside and out and have a full computer science education. And so, to even be able to communicate your ideas effectively, you have to be comfortable with the theory and not just how to plug into an API with 2 lines of code. These scientists are building custom models, really digging down into the math to not only use, but invent new things. And to be able to invent new things, you really need to know the math very well. And so if you're on a team like this, you can't just know how to write 2 lines of code. Your skill set has to be far beyond that. So your theoretical background has to be very solid if you want to be able to communicate effectively with other scientists. Now, a lot of people say, well, I don't ever want to be a scientist, so I don't really care how these algorithms work. Unfortunately, that's a very bad attitude to have in the workplace. Suppose, for example, I am running a business. Now, an employee of mine, he wants to show off and say he's learning about machine learning. He says, oh, I'm taking this machine learning course online, therefore I will become a machine learning master. But his approach to machine learning is to learn as little as possible. He says he doesn't care about the math, he only wants the practical stuff. He only wants to know the bare minimum. He tells me he doesn't care how it works, he's just going to plug into some API, because that's what his buddy told him he could do. As a business owner, I really don't want this guy working for me. I run a business that sells something, and the life of the company itself and the livelihoods of the employees all depend on our products being the best they can possibly be. So if someone comes to me and says, I don't care about being the best, I just care about doing the bare minimum, my response is, I don't want that guy on my team. In fact, he should be fired. So be careful if this is your approach to machine learning. No business owner wants to hear that your approach to the business is to do the bare minimum and to put off some math because you think it's too hard. That's a scary prospect for a business owner. Now, if we go back to our original question, maybe you've realized we haven't answered it yet. What kind of course is this? Well, you can think of it as a marriage between these approaches. We want to cover all the math and derivations because that's very important if you want to be able to communicate effectively with other scientists, to be able to debug your code effectively, and to be able to invent new approaches. This is also what we mean by machine learning. We mean really knowing machine learning and not just programming with an API. So the theoretical background is very important. At the same time, we're not going to introduce 20 different algorithms in the same course, because unlike a typical academic course where you can pass just by understanding 25% of the material, in this course it's structured in a way that if you have any missing gaps, it's going to be impossible for you to move on to the next stage. But academic courses don't contain much coding, if at all. So in this course, every algorithm we learn about will be implemented in code. My motto is, if you can't implement it, then you don't understand it. You can pretend to understand it, and when you talk about it, you might sound like you understand it, But implementation is the true test. It's like a math exam rather than writing an essay. When you write an essay, you might be able to fool the teacher into thinking you understand something. But in a math exam, either your answers are right or your answers are wrong. In this context, either your code works or it doesn't. It's very clear cut. When it comes to practicality, we cover that too. We demonstrate our algorithms both on real-world data like text and images, and we demonstrate our algorithms on two-dimensional data sets so that you can visualize what an algorithm is doing. Both of these are important. Text and images are quite possibly the most practical data there is. Some billion-dollar companies exist and thrive because of those capabilities. 2D data sets are critical as well because as humans, that's the only thing we can see. But at the same time, we don't try to pull the wool over your eyes and pretend like you need 20 different data sets to practice on. Instead, we learn something much more valuable, how to use an algorithm on an infinite number of data sets, because we are able to abstract the idea that all data is the same. Remember that all the computer sees is a list of numbers. It doesn't know that those numbers represent height measurements or an image pixel. And of course, by experiencing both ends of the spectrum, both the theory and the implementation, and then finally plugging data into your model, that's going to make you very well-rounded professionally. To conclude this lecture, I want to pose a final question. How does all this knowledge help you? Why does understanding the approach of this course make you better at machine learning in general? Well, my hope is that this gives you a very high-level, bird's-eye view of the landscape. You can see the different approaches of people from different backgrounds. Academic people typically don't see what other non-academic people are doing, and those people who hate math typically don't see what people who love math are doing. So with this bird's eye view, you can see everybody. If you're learning machine learning, it helps you understand who am I competing with when I apply for a job, and what kinds of jobs are out there, and what would be adequate preparation. If you're hiring for a machine learning team, it helps you understand the different backgrounds of individuals you have to compare to one another to understand their strengths and weaknesses and what they bring to the table. Hey guys, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. Because I now have an entire library of deep learning and machine learning courses, one question I get a lot is, where should I start? I hope this lecture helps you answer that question. First, let's discuss, how did we get here? Now this is a fine place to start, as long as you have the skills to understand what's going on, or you're willing to do a lot of research by yourself in order to catch up. So what are the prerequisites leading up to this course? The very first course I like to call Linear Regression Deep Learning in Python Part -1. This is a traditional linear model from statistics. It introduces you to the form weight times input plus bias, which is used everywhere, even up to convolutional and recurrent networks. You want to be very comfortable with this. In this course, we're able to train our model just by solving an equation. This is the only time we'll be able to solve our problem in closed form. This course also introduces you to basic ways of treating data, like one-hot encoding. The next course I like to call Logistic Regression Deep Learning Part 0. This is another traditional machine learning method, but it does classification instead of regression. In this course, you learn about gradient descent. This is how you train your model when you can't find a solution in closed form. You'll also learn about basic machine learning concepts like regularization and how the logistic unit mimics the biological neuron. These two courses lead into this course, Deep Learning in Python Part 1, which focuses on taking you from binary classification to multi-class classification and the training algorithm known as backpropagation. I want to build strong fundamentals at this stage because all of these subsequent topics on deep learning will absolutely depend on them. In this course, you'll also get a lot of practice with these fundamentals, working on basic problems like XOR and donut, and learning how nonlinear features can be learned automatically, and practical problems like e-commerce and facial expression recognition. So where do we go from here? In this class, you'll learn about basic backpropagation, but there are ways to improve it, like momentum, adaptive learning rates, and using the GPU on Amazon Web Services. This is Deep Learning Part 2. Since you'll need libraries like Theano or TensorFlow to take advantage of the GPU, in this course you'll learn how to use these libraries from the ground up. What's great about them is that they do automatic differentiation, which will allow you to build deeper networks and more complex networks, like the ones that incorporate convolution and recurrence without much extra effort. Of course, this all necessitates knowing about backpropagation first, which is why this is part 1. In part 3, you'll learn about convolutional neural networks, which emulate the animal visual cortex and work extremely well for image classification. In part 4, you'll learn about unsupervised deep learning, which by itself doesn't sound that interesting, but I'll show you how models like the autoencoder and restricted Boltzmann machines can be used to enhance the training of a neural network and overcome problems with pure backpropagation like the vanishing gradient problem. Notice how this also necessitates knowing about backpropagation beforehand. In later courses, you'll learn about recurrent neural networks, which are useful for time series and sequences. You'll learn about deep NLP, which is useful for modeling and understanding language, especially sentiment analysis. This is where the famous Word2Vec will come into play, where you can do neat things like king minus man plus woman equals queen. And finally, you'll learn about reinforcement learning, which allows us to apply deep learning to playing games. A famous application would be Google's AlphaGo. I want to reiterate that my goal in this course is to teach you real skills and strong fundamentals. Deep learning, unlike a lot of the machine learning libraries out there, is not just plug and play. You need to understand what's going on under the hood in order to apply deep learning effectively. If all you want is to learn how to install a library and run these 3 lines of code, then not only will you be unsuccessful in applying deep learning, but no serious company will hire you. Why do I mention this? Sometimes people tell me they're trying to learn deep learning, but there's too much math. Or sometimes they say there's too much programming. Answer this question. Would you join a school for chefs and then complain that there's too much cooking? That's right. Everyone would think you were crazy. Deep learning is a specialized topic in computer science. Computer science is math, and computer science is coding. Approach this as an exciting challenge, not a burden, and you will find the results very rewarding. Hey everyone, and welcome back to this class. In this lecture, I'm going to answer a question that I get pretty much multiple times per day, and that is, what order should I take your courses in? This is a great question, and it's something that even I have to think about sometimes. What is the best way to learn all this stuff? So I think that what you'll find is, this ordering makes a lot of sense in that we're always building on skills we learned before. So it's just like learning calculus. First you learn calculus 1, then you learn calculus 2, which is kind of the opposite of calculus 1. Then you learn calculus 3, which expands on the ideas from both calculus 1 and 2. And then from there you can go on to even more advanced topics like probability. So this is a process based on skill building. Now it's important to keep in mind that this lecture is not just about my courses and how to navigate them, although that is the question I'm answering, since that's a question I get multiple times per day. But this is also a lecture on how different machine learning topics are related and what depends on what else. So even if you end up not taking any of my courses, it doesn't change the fact that these topics are still related to each other in these ways. So in some sense, this lecture isn't really about my courses at all. It's a general lecture about how different types of machine learning models are related and in what order you might want to learn them from a skill building perspective. Now I want to show you this stuff in a visual way. I've actually set up a web page where you can go to and look at the chart I made for yourself. So what I want you to do is go to this website, deeplearningcourses.com. Now I want you to click on the catalog link. And from there you want to click on the click here link. Okay, so this brings us to the course order web page. So at the top you have sort of this linear chart. Right, it's just one course after the other after the other. But this is not really what I want to look at in this lecture. This linear chart gives you a basic overview, but it's not ideal. The reason is, the relationships between courses are way more complex than this. Sometimes one course gives you the skills you need for 2 other courses. Sometimes there will be a course that's so complex that it depends on multiple different courses. So this is the perfect opportunity to use a graph. So if you scroll up at the top, you can use this link to just jump down to the bottom, and we have this graph where you can see the dependencies between each course. So what I'm going to do is I'm going to go through each link in this graph and explain to you why it exists and why it's important. So let's look at the SQL course first, since that has no links. So it might show up in the middle, so you can just drag it out to the side. That's the coolest thing about this graph, because you can just pick stuff up and drag it around. It's very interactive. So SQL has no links. This isn't a prerequisite to any other course, nor is any other course a prerequisite to it. It is standalone. You can take it at any time. Next, you'll notice that there are courses that have no links going into them. So for example, the NumPy course. This is because none of my other courses are a prerequisite to this course. This course was just designed to give you a basic understanding of the syntax and tools we use in data science and machine learning. The goal is actually to not do any machine learning in this course. Believe me, it was actually quite difficult to accomplish that because it's so easy to use something in machine learning as an example. It was very hard to avoid talking about it. You'll also notice that there are some courses with no outgoing edges. You can think of these as the most advanced courses. They are at the top of the ladder. So for example, this one right here. Of course, that could change in the future as I create more courses, in which case I will update this lecture. So let's start with what's coming out of NumPy. You'll see that there are two links. One goes to linear regression, and one goes to Bayesian machine learning A/B testing. And by the way, you can zoom into this graph, so that's what I'm going to do right now. Okay, so here's linear regression, here's Bayesian machine learning. So while NumPy goes to both of these courses, I'd actually strongly recommend linear regression as the next step. Bayesian machine learning doesn't depend on any other courses per se, but it's still more advanced. It requires a more advanced understanding of probability and of real-world engineering problems like optimizing the click-through rate of a link on your website. So linear regression would be my #1 recommendation for your foray into machine learning. Now after linear regression, we have logistic regression. So why do we go from linear regression to logistic regression? Well, the basic idea is both of these are linear models. In other words, the model is of the form y equals mx plus b, which is a line. The difference is that linear regression does regression, while logistic regression does classification. We want to learn classification because that's one of the central tasks of a neural network, which is what comes after. And you might notice that linear regression also has two outgoing links. So there's one to logistic regression and one to reinforcement learning. This is because my reinforcement learning class makes use of linear regression, so naturally, if you don't understand linear regression, you won't understand that part. But again, this is a much weaker link than going from linear regression to logistic regression. This is because reinforcement learning is actually conceptually more difficult. It doesn't depend on the content of any other courses directly, other than what we've shown, but the ideas behind it are more advanced. You really want to have some experience with both supervised and unsupervised learning before jumping into reinforcement learning. It helps to build the proper perspective on the subject. We will get back to reinforcement learning later, but for now, let's go along the deep learning path. So on the deep learning path, we last discussed logistic regression. This is also known as a neuron. This is very important because in order to build a neural network, we must first know how to build a neuron. A neural network is just a bunch of neurons stuck together. So this leads us to Deep Learning in Python Part 1, which is the bright green logo. This course teaches you how neural networks work and basic fundamental operations like backpropagation. Once you know the basics of deep learning, you can move on to Deep Learning Part 2, or Modern Deep Learning in Python. This is the same image, but in a darker color to signify that it's a continuation of the previous course. As the title suggests, this course is all about modern developments in deep learning. So we go over ways we've improved basic backpropagation, like momentum and adaptive learning rate techniques like RMSProp and ADAM. We talk about modern regularization techniques like dropout and batch normalization. And most importantly, we look at modern deep learning libraries like Theano and TensorFlow. We also take a look at Keras, PyTorch, MXNet, and CNTK. You'll see that once you know the fundamentals, things don't change that much from one library to the next. It's all the same concept. Now, learning about these modern libraries sets the stage for the next level, which is applying deep learning to certain special data formats. The two fundamental types of data are text and images. These are special because they have unique structural properties, and we can make use of our knowledge of those properties in order to build better neural networks. For example, we know that text is made up of sentences, and sentences are sequences of words, so sequential modeling is important. We know that images are two-dimensional objects, but importantly, each pixel is very likely to be the same as nearby pixels. For example, if you pick a random pixel on an image of a red car, if that pixel is red, then most likely the pixels around it are also going to be red. There is also no question about the practical applicability of text and images. The internet is made up of text, so by doing machine learning on text, you're learning techniques that essentially allow you to write models of the entire world's knowledge. Images are also everywhere. Snapchat, Instagram, Facebook, self-driving cars, home security systems. Knowing how to deal with images is super important, and billion-dollar companies exist because they are good at it. So that brings us to the next course in the deep learning series, Convolutional Neural Networks, or Deep Learning in Python Part 3. This is all about how to incorporate convolution into neural networks and what convolution is in the first place, and how that helps us make use of the structure of images. Let's scroll up a bit. So after convolutional neural networks, we take a detour into unsupervised deep learning. Unsupervised deep learning isn't very popular with beginners, but it should be. If you look at the experts of deep learning like Yann LeCun, Yoshua Bengio, and Geoffrey Hinton, they all talk about how important unsupervised deep learning is. This course introduces us to several new ideas. First, the idea of latent variables or latent causes. These are factors that you don't directly observe in your data, but that you can learn about by studying the structure of your data. Second, modern techniques for data visualization like t-SNE. This will be very important since, as I discussed earlier, along with images, text is a really important data format. In order to visualize text in later courses, we will be making use of t-SNE, so it's good to know what it is and why it's useful. Third, unsupervised pre-training. Unsupervised pre-training is the foundation of modern ideas like transfer learning, and we make use of it both in NLP and with convolutional neural networks. Fourth, the vanishing gradient problem. We demonstrate the vanishing gradient problem directly so you understand where it comes from. Vanishing gradients are especially important in the context of recurrent neural networks. And it just so happens that recurrent neural networks is the next course in the deep learning series, Deep Learning in Python Part 5. So recall that our two fundamentally interesting data types are text and images. We've looked at images, and in this course we start to look at text. Why might that be? Well, recurrent neural networks specialize in modeling sequences, and text is just a sequence of words. So it's the best type of data to use to demonstrate the principles of RNNs. Once we've studied RNNs, we can go even deeper into how deep learning can be used on text. That's the next course, Natural Language Processing with Deep Learning in Python, or Deep Learning in Python Part 6. In this course, we look at a very important concept called word embeddings. These allow us to turn words, which are categorical variables, into vectors, which are numbers that a neural network can read. This is why it's very important to have studied unsupervised learning before this, because finding word embeddings is actually an unsupervised task. Word embeddings also allow us to make use of pre-training, which was discussed in Deep Learning in Python Part 4. In this course, we also look at a very advanced model for doing sentiment analysis, called a recursive neural network or a tree neural network. This is an example of a dynamic neural network because it changes its structure based on what input you give it. Most deep learning libraries are not equipped to handle dynamic neural networks, and I demonstrate what happens if you try to build one the naive way. You basically end up building a separate neural network for each of your training samples, and it's going to eat up all your RAM and make your computer slow down to a crawl. So you get a first-hand perspective of why working with dynamic neural networks is not easy. But luckily, we are able to make use of our knowledge of recurrent neural networks, and remember that's the prerequisite to this course, in order to convert a tree into a sequence, which an RNN is capable of handling. So that's why RNNs is a prerequisite to this course. Now you'll notice that this course, Deep NLP, has no outgoing edges. This is because it's the most advanced course that I have on this path for now. I certainly plan on expanding in this direction in the future. However, this is not the last deep learning course in the series. After this, we have deep reinforcement learning, which is Deep Learning in Python Part 7. With that said, I think now is a good time to go back and start exploring the reinforcement learning path. So you'll notice that I have Bayesian machine learning feeding into reinforcement learning. On the surface, these two courses might seem unrelated, but there is a very important concept you'll learn that applies to both, called the explore-exploit dilemma. In Bayesian machine learning, you learn this idea in the context of trying to optimize a click-through rate or a conversion rate, or in other words, the number of times people buy things from your website versus the number of times people visited your website. Very practical concept, I think, if you do anything related to e-commerce. Now, in reinforcement learning, we look at the explore-exploit dilemma again, but in the context of playing games. Reinforcement learning is like a third branch of machine learning, whereas the other two are supervised and unsupervised learning. The main difference is that supervised and unsupervised learning look at static data. In reinforcement learning, the idea is more like you have a robot living in the real world. It can take the experiences it had today, and based on them, behave more intelligently tomorrow. So the learning paradigm in reinforcement learning is sequential. This is opposed to supervised and unsupervised learning, where your dataset usually resides in some file on your hard drive. So in reinforcement learning part 1, we get all the basics, as you might expect. This is a prerequisite to deep reinforcement learning, since deep reinforcement learning applies those concepts to more difficult games. But you'll notice that this is not the only prerequisite to deep reinforcement learning. As the title suggests, this is also dependent on knowledge of deep learning, in particular, convolutional neural networks. But as we know, in order to build a CNN, we have to know how to build a regular neural network, which means we have to know what a neural network is and why it's useful, and so on. So in deep reinforcement learning, these two paths converge. You combine your knowledge of both reinforcement learning and deep learning in this course. Now the reason it depends on CNNs and not, say, RNNs, which is over here, is because we'll be learning to play visual games. So for example, we can learn how to play a video game like Pong or Breakout, which are classic Atari games from the old days. And so those are images because they're basically screenshots from the screen. In the future, we might end up applying RNNs, in which case RNNs will become a prerequisite to that course. So that's the end of the reinforcement learning path for now. I'm very excited to bring you more updates in this area in the future. Let's now jump back to logistic regression, where we can see another outgoing edge to supervised machine learning. So why is this edge here? Well, you may recall that linear regression and logistic regression are both linear models that do regression and classification respectively. These are both supervised learning tasks. And so it makes sense that now that you know one model for regression and one model for classification, it's time to dig deeper into supervised learning. The thing with linear regression and logistic regression is that they aren't really different models, they're both just a line. Because they do different tasks, the techniques and interpretations are slightly different though. And there are, of course, different models that are not linear models that can do these tasks, and that's what this course is all about. In this course, we look at classic supervised machine learning techniques like k-nearest neighbor, decision trees, the perceptron, and the Bayes classifier. Much like how logistic regression was the basic building block of the neural network, classic models like decision trees are the basic building block of ensemble methods. So that's why this course is a prerequisite to ensemble machine learning. Again, we use the same logo with a different color to signify that these two courses are very closely related. In Ensemble Machine Learning, we learn how to combine multiple decision trees in different ways in order to make some very powerful classifiers. What's really remarkable about these methods is that they are very easy to plug and play on data. So if you're looking for a plug and play solution without having to learn a lot of theory, then deep learning is most likely not for you, but ensemble methods are a great fit. Deep learning is very dependent on hyperparameters, and if you choose incorrectly, your model will perform very poorly. Sometimes it requires immense computing power to find good hyperparameters. This is an active area of research. It is not yet solved. This is why you can implement what you see in a deep learning paper, but suppose the author left out some seemingly insignificant detail, so you end up having to make an assumption, and then your results end up totally different. So deep learning is fragile. But luckily, ensemble methods are not. We focus on two very famous ensemble methods, the random forest and AdaBoost. So that's everything on the supervised machine learning track for now. Next, we see an edge going from supervised machine learning to unsupervised machine learning, in particular cluster analysis. The reason we study supervised learning before unsupervised learning is because unsupervised learning is a little more abstract. It takes more effort on the student's part to realize why it's practical and what it can be used for. Cluster analysis shows us how to model data that does not come with targets. As you might guess, we do this in the form of clustering. The idea behind clustering is very simple. We want to know how many naturally occurring groups of data there are, and what are the relationships between the data in these clusters. So for example, if you were clustering books, you might find a book about Steve Jobs and a book about Elon Musk in the same cluster. This cluster is probably about tech companies in Silicon Valley. But you don't need a label in your data to tell you that. You can discover it yourself by looking at how the data naturally groups together. Now, as I mentioned earlier, I think once you learn about both supervised and unsupervised learning, you'll be ready to jump into reinforcement learning. I haven't made cluster analysis a prerequisite to reinforcement learning since none of the material depends on this course, but it's good to know about these techniques so that you have a more mature and experienced view on machine learning. What is sort of a sequel to cluster analysis is hidden Markov models. The reason might not be clear at first, so let me give you two reasons. Number one, they are both unsupervised machine learning models, just that HMMs is harder, so it's natural to learn about clustering first. Clustering is also about static data, whereas HMMs are about sequences, so it's similar to the process we did in deep learning. We looked at static data like images, then sequential data like text. Reason number two, in cluster analysis, we learn about a technique called the Gaussian mixture model, which we make use of in the HMM course. One key point is they both learn by using the expectation maximization algorithm. So it's good to first see the EM algorithm on a simple model, and then when you see EM again on a more complicated model like the HMM, it won't be as intimidating. One key concept you learn in HMMs is the Markov assumption. That just means the current state depends only on the previous state, but not any states before it. This is a simplifying assumption that usually makes the math easier to work with. You will also notice that we encounter the Markov assumption in reinforcement learning. However, it's not too hard to learn it from scratch. And so for that reason, I do not consider HMMs to be a prerequisite to reinforcement learning. The Markov assumption is really the only thing they have in common. There is also a slight connection between cluster analysis and unsupervised deep learning. So I'm not going to draw the link right now, but I sometimes consider this to be unsupervised machine learning part 1 and this to be unsupervised machine learning part 2. We also see that HMMs feeds into the RNN course, which is about deep learning. So why might that be? This is of course because both these models are models that can learn about sequences. In particular, in both these courses we model text as sequences. But whereas the HMM makes use of the Markov assumption, the RNN does not, and hence the RNN is a more powerful model. And so this just goes along with the main theme that we always go from simple basic models to more complex models. This is also something you should do in your work as well. If you start with a simple model, you often find that it is faster and more robust. Complex models sometimes break down, but they are also more difficult to implement and might not even be fast enough. Of course, that's just a generalization, so you always want to analyze engineering trade-offs individually for every problem you have. Now, there is one last link in this part of the graph here that I want to explain, and that's the first NLP course. You can see that it depends on supervised machine learning and feeds into deep NLP. The main purpose of this basic NLP course is to apply basic machine learning models to text. So that's why supervised machine learning comes before it. It's because that this course was all about basic machine learning models. The important skill for NLP was not the implementation of those models, but rather a bigger picture perspective on how machine learning is used. What is the interface between the data and the model? What does the model do? What is its input and output? How is the output interpreted? And so we take those principles and we apply them to text. In this way, we can see that text can be treated in such a way that you don't have to think about it any differently than any other data. This reinforces the principle that all data is the same. The machine learning model doesn't care what your data is. All it sees is a table of numbers. It doesn't care if it's text or images or radar signals from space. The model just does what it was designed to do on the numbers that you give it. So this course gives you a high-level systems perspective on working with machine learning models in text. This easy NLP course also feeds into deep NLP, which is of course not so easy because it depends on a lot of background in deep learning. One of the main questions I get in the NLP course is, how do I improve the results of these basic models? And a lot of the time the answer to that is, well, you have to use a more complex model, but of course that necessitates learning how that complex model works. And deep NLP is an example of that because we learn a state-of-the-art method for sentiment analysis, whereas in easy NLP, we used only a linear model. So it's important to understand that while yes, it's possible to improve the predictive ability on simple basic models, as you can see, it's not always an easy path to get there. So you have to make sure you're prepared. Case in point, just look at all the time spent just to get to deep NLP. It's not an easy task. Let's now scroll over to GANs and variational autoencoders. Just like how deep reinforcement learning is not related to deep NLP, this isn't really related to deep reinforcement learning either. This is Deep Learning Part 8 by order of creation only. It is the spiritual sequel to unsupervised deep learning, which was Deep Learning in Python Part 4. Okay, so just to reiterate, this is Part 6, Part 7, and Part 8 by order only, but they are not related to each other conceptually. Although it's always nice to know all these things because more context makes future things easier to learn. So the reason this is linked to this is because GANs and variational autoencoders are also unsupervised deep learning models. But whereas unsupervised deep learning was all about how to improve supervised learning, GANs and variational autoencoders don't have any direct benefit to supervised learning at all, although we do make use of supervised learning within the course. In this course, the focus is on generating images. We've seen that GANs can create photorealistic images based on a dual neural network system. That's pretty cool because before GANs, we didn't have any kind of machine learning model that could generate real-looking images. Nowadays, GANs are able to generate high-resolution, high-quality images of people that you can't even tell are not real people. It certainly makes the idea of the matrix seem very possible. Alright, so I hope you found this lecture helpful. We saw that these courses are related to each other in some pretty complicated ways. Learning machine learning is not exactly linear. Sometimes you have to take one course before you can take the next. Sometimes one course might just be related to another course by some key concept, but maybe in one context it's a lot easier to understand. So remember to keep in mind that these arrows do not all indicate strong prerequisites, but rather there's just a relationship between the two courses. I hope that this lecture explained any nuances between what is a prerequisite and what is not, and I hope I did a good job of answering which order should you take these courses in and why.